And now, what can I say about the value of that? Let's kind of look back. So if I'm remembering correctly, yesterday we got into how to use the definition of the derivative on a rational function.
Yeah, and we did a quotient, or not quotient, sorry, and a...
We're not doing quotient rule till next week.
Right.
All right. So guys, with this function, if I asked you what is the slope of the tangent line at x equals 2, really I'm saying what is f prime of 2? Yeah? And if I asked you guys what that is, you would say? Negative 3/4. Sweet. All right. Now, find the derivative using forward difference quotient of y equals the square root of x. So we would be taking the limit of what?
Square root of x plus...
Before as delta x is approaching 0, we would do the square root of x plus delta x minus the square root of x all over delta x. And if we found this limit right now, we would end up with 0 over 0, yes? Does anybody have any ideas on how we might be able to figure this out? Should feel very conjugate. We're going to do the conjugate of the top. Typically, guys, when we have square roots and we end up with 0 over 0, that's how you, that's when you use the conjugate. And, guys, when we do that, what are we going to have on top?
Why are you multiplying it by?
Conjugate.
The conjugate of the numerator.
Oh, there was the multiplication.
And so what do I have in the numerator now? X plus delta x minus x. And then on the bottom we have delta x times that whole expression. Okay. Maybe we'll see that those x's cancel out. And then maybe we'll see that the delta x's that are remaining can cancel out. And so I have a 1 on the top now. So really this is saying the limit as delta x approaches 0 of 1 over the square root of x plus delta x plus delta, or the square root of x. Are we feeling okay with this? Okay, so what is the slope of the tangent line?
1 over 2.
2 root 2. Which, if this is bothering you, I understand you can call this root 2 over 4, because some people might see that square root in the bottom and want to vomit. You can multiply by root 2 over root 2 and get square root 2 over 4 if you wanted. I don't see myself being picky about that.
It's okay now.
Unless we're using it, it's fine. There might be times where we need to use that slope where you might want it to be simplified. But I don't know that you'll have to. That whole rule about not having radicals in the bottom of a fraction, it made sense 25, 30 years ago when we didn't have calculators that could approximate what that function very well. Way back when Miss Meister learned about radicals, it made sense. It doesn't make sense now. But you should be aware of it because, ACT, SAT, GRE, college professors might care. How are we feeling? Okay. Next, we're going to do the alternate form of the derivative. By using the alternate form of the derivative, guys, this can be really useful when our functions are not Nice. Does that make sense? Okay. So, guys, what do you like, as we think through, what does the absolute value of x look like?
Y.
Okay. And so if I ask you what is the slope that at x equals 0, this is starting to look a little bit meh. It's not smooth at x equals 0. It's like a sharp point. Well, it's non-differentiable on the whole, right? But we can differentiate it from both sides. So now so this alternate form of the derivative gives us the opportunity to look at it, when the derivative might not be a pleasant thing to look at. Does that make sense? All right. So for example, we might say, well, what is the limit as x approaches 0 from the left? And so that would be the absolute value of x minus 0, yeah? Does this make sense? Over x minus 0. And if I'm approaching 0 from the left, what is the value of this?
-0.
Negative 1. Top would be positive, bottom would be negative, otherwise they're the same thing, yeah? And you guys, what is the slope of the left side of the graph? -1. That makes sense, right? That the derivative would equal -1. All right. Then the limit as x approaches 0 from the right of absolute value of x minus 0, absolute value of x minus 0. What would we get? +1. And again, that kind of makes sense as we look at this. Now, by using the limit as we approach, we're finding the differentiability of the function everywhere but that point in the middle. The value of the derivative at x equals 0 is not there because it's not differentiable at x equals 0. Cool? All right, let's look at this one real quick. What does the function cube root of x to the 1/3 mean? Cube root of x looks like this. Though that's not the best rendering of it. Let me try again. How'd I do? It's definitely better. It's just like a weird sharpness. Okay. So what is the derivative? Where do we have like weirdness in our tangent line? What would you say?
0.
X equals 0. So we're going to say, well, what happens as I approach 0 from the left of x to the 1/3 minus f of 0 would just be 0, yeah? Over x minus 0. What am I going to get?
Like a negative tiny number over.
If we are taking the cube root of numbers smaller than 1, would it be bigger or smaller? Bigger. So, for example, the cube root of 0.125 is 0.5. Everybody with me? So it went up. So in between, radical functions outside of 0, taking the root of it makes it bigger. Or makes it smaller. Inside, I didn't say that well at all. At all. You guys, let's pretend that didn't happen the way I just said anything, because that was terrible. Okay, outside of -1 and 1, when I take a radical of a function, of a number, it gets smaller. In between -1 and 1, when I take the radical, it gets bigger. Are we Is that okay now? Because I said that really terribly. Really, really terribly. Yeah. Okay, so knowing that, this answer is infinity. Top and bottom are both going to be negative, right? Okay. What about if I do that from the right?
Same thing. It should still be positive. 'Cause
It's still going to be not. The top one is a negative over a negative. The bottom one is a positive over positive. And the top, at x equals 0, the top is rising faster than the bottom. Or Now, what does that suggest about the slope of my tangent line at x equals 0?
There's a vertical asymptote.
It's kind of, it looks like what a vertical asymptote is. Now, the slope is, so it's almost like that tangent line, I should do it in a different color here, is a vertical tangent line. So the derivative doesn't exist there. But like this one, it doesn't exist because we end up with like that sharp turn, like the absolute value one. We end up with like that sharp turn cuspy vibe of why the derivative doesn't exist at that one point. Here we have the fact that the tangent line would be vertical. Are we doing okay? Okay. Lastly on this slide, y'all, we want to draw a graph of the derivative of the function. Cool? So to do this, if I'm drawing a graph of the derivative, I'm going to pick a few points and estimate what is the slope at those points, since the derivative is the value, or is the slope at any given point. So for example, if I look at, say, this point right here, what does the slope of that line look to be? Give or take. 1. So I'm going to go ahead and make a point at 1, because that's, but that's not at 1. You guys, look at my scale. If this is 2, this is 1. Yeah? All right, and if I pick that matching point on the other side, what's the difference? -1. Okay, we might want to look at, say, this one, that vertex. What's the slope of the tangent? Like, what would the tangent line at 0 look like? Or at the vertex look like? It'd be horizontal, which is a slope of 0. So can you guys kind of see this? Like, my derivative is this line right here. Now, you guys, what is the original graph? What kind of function?
X squared.
It's of the form x squared plus ax plus b, or whatever, however you want to think of it through, yeah? But it's definitely a parabola. There might be something in front of that x squared, but in this case there isn't. Okay? Now, what is the equation, if I ask you guys to come up with the equation of the derivative? Y equals 2x minus 3, yeah? Does that, in fact, we could even now say that this is probably a -3. But you guys see how, like, it fits from what you already remember of derivatives? Does that make sense? All right. What about this one?
You
Well,
would
there'd be
have a
like no
hole,
point,
right?
yeah, no point at
Hole.
0.
At x equals 0, the f prime does not exist. Okay. Now, do we know that it's a hole versus an asymptote? No. We don't know yet. Okay. So let's pick a point. I'm going to pick this one. Looks like maybe 2/3 to me. Give or take. Like, to me, it looks like So 2/3 would be here. I'm gonna do it in purple. Okay. What about here? Maybe 2, give or take. Obviously, I'm going to be looking much more for general forms here on this one. And maybe one more out here. Let's do this one. Maybe 1/4. Should be like here. And I'm starting to get a vibe that it's looking kind of like this. Are you guys with me that the red graph here seems to always be increasing? So the slopes, any tangent line would be a positive slope. Whereas over here, any tangent line would be a negative slope. Okay, so that cusp in this particular case is looking to me like an asymptote. And in fact, it's symmetrical, so I'm going to kind of flip some of these points over. And now, is every cusp going to be an asymptote? I don't know if I feel comfortable saying that yes or no. It kind of feels that way because of positive versus negative to get a cusp like that. But certainly not differentiable at the cusp, but near it. How are you guys feeling so far? Pretty good? All right. So let's talk about some really basic forms of some rules for taking derivatives. We're going to get as far in this as we can, okay? All right. Constant rule, you guys. The derivative of a constant, I'm going to use 2. Think about the function f of x equals 2. Here's my axes. F of x equals 2. It's horizontal. Yeah? At at y equals 2. Yeah? Okay? What is going to be the slope of the tangent line at every single one of those points? 0. So the derivative of any constant is 0. Okay. The power rule, I'm going to ask you guys to think through, because a power rule is like, it could be x squared, or it could be x to the 3rd, or it could be x to the 4th, which is like a little bit fatter and like sharper than x squared. Those are all power expressions, okay? So if I have find the derivative of something to a power. Does anybody remember how we find it? Turn this into n to x to the n minus 1. Yeah? Do I need to explain that, or are we comfortable with that? Okay. Constant multiple rule is saying what is the derivative if I'm taking something like 3x. 3. So if you have a constant in front of your x, the value of the derivative is just that constant. Again, y equals 3x is a line, so the slope is the same all the way through, and that constant is that slope. So the derivative of the slope of the tangent line would match the slope of the function. Cool? All right. Lastly, if I say to find the derivative of f of x plus g of x, you can just separate that out. That's like saying what is do the derivative of f of x plus the derivative of g of x. You can all right. So typically when it comes to notation, y'all, I'm going to ask you to be consistent with the notation I've given you. So, for example, we're going to find a bunch of derivatives relatively quickly today. For this one, for the notation, I would like you to use dy dx because it's in the form y equals. And so you're taking d dx of both sides. Is this okay? All right. So, how many of you believe that you can find this derivative relatively quickly? Prove it. Thumbs up, thumbs down. We all feeling good about this? Okay? Cool. So this one, because I give it to you in this functional notation, I would like you to use f prime of x as your notation. Am I going to get really picky about it? Definitely not. But it's like the general trend in what you might expect from future math professors is consistency amongst the notations. Does that make sense? I do have a slight preference for dy dx, I suppose, in terms of where you guys might go within the calculus world. Dy dx, getting comfortable with that notation is actually really useful. What's this one? 1/2 x plus 3, right? No. Okay. All right, what if I give you this one? No.
You could just multiply it by the x.
Are you with me that this function is equivalent to 3x plus 4 minus 5 over x? A souped up pickup truck that had a purple racing stripe. We all make choices, guys. Do you really want to use the quotient rule on this?
I guess not.
I hate the quotient rule. Never learned it. We'll talk about that when we get to it. Like now I know it because I've taught it. But I always just did a combination of the product rule and the chain rule instead of doing the quotient rule. So I would, every calculus test, I would prove the quotient rule. Write the proof for it so that because I could never remember which one was which. On what side of the subtraction sign. So I just wrote the proof every time.
I just had Miss Lombardi yell her, like, pneumatic whatever at me enough times that I remember it.
Yeah, she sure does love it. All right, and are you guys comfortable with me saying minus 5 over x is equivalent to minus 5x to the negative 1?
Yeah.
Okay. Because that sure does make that power rule a little bit easier to work through. So, are you guys doing this right now? Should I give you a second to do it?
No.
Are we ready for me to just be like, oh yeah, this is definitely 3 plus 5 over x squared?
Can you write as x to the negative second power?
No. I would go back to consistency if I give it to you as a... If I started out as a rational, I would expect you to leave it as a rational. What's the trick you need to remember for this one?
So the x root x.
The 3 root x is 3x to the 1/2. All right, I'm going to make you guys do this one without me. And did I get it right? Are you sure?
It's not.
I think so.
I feel like I'm more rusty than you guys are at taking derivatives.
I think that's right.
Sometimes I make Lambo check my derivatives because I don't trust my work.
That's right.
So,
That's right.
yes, it is.
Yeah, okay.
I was thinking it had to be like flipped in some way, but it doesn't.
All right. Correct, it doesn't. Hey, y'all, what's the derivative of sine x? Cosine of x. What's the derivative of cosine x?
Negative sine of x.
What's the derivative of e to the x?
E to the x.
Everybody's favorite.
They're just chilling.
Yep.
That feels like a Lombardi thing to say. E's just chilling.
Yep.
All right, cool. I've got a couple practice problems for you guys to do here.
I don't think she actually said that, but no one mentioned it to her.
I can just hear her saying it. You guys, she turns 40 on Sunday.
Happy birthday.
You guys, after we do these two, do you want to just like bomb her class and sing her happy birthday?
Yes.
Doesn't that sound like fun?
Yeah.
Sure.
Oh yeah, we'll be fine. Should we do these, all of these examples? Like we should get through the notes, I guess, and prioritize that, and then go do it.
Is she even in there?
I know it'll be
Ian had classes.
Beams in their 5th and 6th.
What if we do A and B then?
Will you be able to refocus back down if we?
No.
Yeah. So let's get through the notes. Let's get through the notes, and then we'll do it. But we now have even more motivation to get through the notes.
It's not actually a regular.
It's on Sunday, but we won't be able to.
Yeah, we won't be there for this.
And it's 40, you guys. She's like old now.
How old are you?
Older than that, but hey,
The way you asked that is
Like nonchalant.
just ever so slightly older than that. Did you guys do this?
Yeah.
Yes.
I think so.
Oh, I forgot what I did.
I did. I did. Or you did. But I remember.
How'd I do?
Isn't it plus cosine? Because the derivative
No.
of sine is negative sine.
The derivative sign is not negative.
Yeah.
It's
So yeah, that's what I got.
everything that begins with a C, the derivative is negative. But the sign does not begin with a C. And then this one, 3 to the x.
The interruption. Morgan Gladman, please come to the main office. Morgan, please come to the main office.
How'd I do?
Yeah.
Good. Yes, I agree.
Thank you. Had to was 9 for a second. I don't know why.
There was. I'm not gonna get off track.
Cool. You guys, what's velocity?
The derivative of
No.
meters per second. It's
I'm
not
not in
acceleration, so I'm just putting that out.
Just in general, like in a non-mathy, sciencey world, I say, what's the velocity of, I don't know, a souped-up pickup truck with a purple racing stripe going down?
How fast?
It's at speed,
How
yes.
fast it's going
It's
in one
change in
direction.
position. It's the change in position over the change in time.
Where's the
Vector, acceleration.
Position.
She said velocity.
Yeah, but then.
Yeah.
Position.
Okay, if it's speed, then it's speed.
Yeah,
There's,
acceleration.
I don't know what gives after that.
I know there's something after.
Okay.
There is.
Something before velocity.
Position is what's before velocity.
Yeah.
Okay.
But there is something after.
So you guys, here is the position of a billiard ball that's getting dropped from a height of 100 feet. That feels like it's going to shatter. What is its, how long does it take to hit the ground?
The derivative.
No, because we already have the equation. We can just plug it in.
It would be 0 equals negative 16t squared
Yeah.
plus 100, yeah? Because if it hits the ground, its height would be 0.
Square root of 100/16.
Which is 10 over 4, 2.5.
Wait, why? Does it equal 0? Like I did the
Because what's the height of the ground?
0, but,
So if we're trying to find the time
Yeah.
where the height equals 0.
oh, okay.
So
What are you trying to do?
this is in feet, yeah?
Yeah.
2.5 seconds,
Oh, you're doing.
right?
Oh, that's time.
Well, oh, come on, Meister. So the average velocity would be at 100 feet. In 2.5 seconds. So the average velocity is 40 feet per second. All right. Now, is it always going 40 feet per second?
No.
No, what happens when you drop something? It accelerates, right? And so it starts going slow, 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 and then fast, 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 fast.
Yep.
Did you guys like how technically I described that?
Yes.
I can't think of a more technical definition than that. Okay, so could we find the average velocity in between 1 second and 2 seconds? Well, we could say, well, what is S of 1? What is S of 2? And I think we get 84 and 36. But if you guys wanted to double check that arithmetic, that seems like a smart thing to do.
I actually don't want to check that.
No, you're right.
So on the interval 1 to 2 for time, so in between 1 second and 2 seconds, it went, it fell 48 feet over 1 second. Yeah? So 48 feet per second. Are you guys comfortable with that?
Yes.
Yes.
I agree with that.
Everything was control.
And then S of 1.5 is, we're getting to the point where Miss Meister trying to do stuff in her head is going to go poorly. Let's see. That would be 2.25 times negative 16 would be 4 times 9 is negative 36. I think it's 64?
76.
64.
Yeah,
64.
64. Okay.
And so then it went 20 feet in 0.5 seconds, which is 40 feet per second. Am I doing, is this feeling okay? Okay, and then for instantaneous, or for over 0.1 seconds, so we would have to find S of 1.1. This is when,
80.64.
what'd you get?
80.64.
80.64. And that's from 1, so that's a total of 3.36. Over 0.1 would be 33.6 feet per second. Am I doing okay with this? Okay. So what if, so essentially, if I'm trying to figure out how fast is it going at exactly 1 second,
Derivative.
I essentially need to take the limit as we're getting closer to t equals 1, which is the derivative at t equals 1. Well, what is s prime of t, y'all?
32.
Negative 32t. So what is the instantaneous velocity right at
1 second.
t equals 1?
Negative 32 feet per second. Well, I'm sorry, just 33 feet per second, because whatever.
Now, you guys looking at our average velocities as we get closer and closer and closer, does that feel good to say 32? Yeah. As I look at what's happening to my velocity as I get closer to 1 second is approaching 32. Okay, so some big ideas. I think you guys already know this from the sounds of when I said what is velocity. Okay, we typically use s of t to describe position. S prime of t is equal to the velocity at t. Because it's the rate of change of your position is moving. What is the rate of change of your, what's v prime of t? That's describing how the rate of change of your velocity is your acceleration. Yeah?
The acceleration was yeah. That must not. Yeah.
I'm not going to make you go past that, but what is a prime of t? Jerk. Think about when your car's acceleration changes, your whole head
Jerk, that's what
jerks.
What's yaw?
Yeah, it's like when you fly.
Yaw is like right to left movement or something.
But it's like one of the angles you are.
Yaw with a, with a
W.
W?
Yeah,
It's like yaw, pitch and roll.
All right, y'all. You know what? We're going to finish this problem on Monday.